Hi. Oh yeah, kids. Hi, kids. Hey, I want to show you a real quick, amazing demo. See, I have a sheet of paper here, okay? And if I take and I blow over the paper, what? The paper goes up. I know. It's not a trick. It's physics. Um, so I'm going to do a little video on why that happens, and it relates to something called the Bernoulli Equation. And hopefully this video won't totally blow. Sorry. So let's talk about that. So Bernoulli Equation talks about fluids that are moving. Okay. Now, how could the fluids be moving? Well, they could be moving through, a pipe, and maybe the pipe is getting wider, like this. So maybe the fluid it's moving through, and then it's going to go slower over here because of the equation of continuity. Hey, maybe the fluid is going downhill. Okay. Hey, maybe the fluid is, I don't know, going uphill. You're pumping water to the top of a building, but it's going to get narrower, because it's because you don't want these really wide pipes at the top of a building. But in all of these cases, you're going to have a moving fluid that the speed is going to change or the height is going to change. And hopefully, if you're thinking, speed is changing, height is changing, what physics concept deals with change in height, change in speed? Oh, right! Conservation of energy. Okay. So really, the Bernoulli equation is just conservation of energy. So let's treat this like conservation of energy. Okay. So let's say in any of these examples, what do we do when we have conservation of energy problems? Well, any problem at all in physics, we draw a picture. All right. So maybe this is our picture. Maybe this is our picture. Maybe this is our picture. Well, what do you do when you have your picture? Then you label your important points. Well, we'll call this point A, and we'll call this point over here point B. Maybe point A is up here, point B is down here. Maybe point A is down there, and point B is up here. So, hey, there's my different pictures. Like I could be like this, I could be like this, I could be like this. So I want to show you just in general so that, it's not specific to any case. But so here's what you do. You say, well, let's pick, I don't know, like this one, for example. Okay? Or this one, for example. All right, so remember when we're doing our conservation energy, you draw your picture and then you go, hey, well, where am I going from? I am going from A to B. And then you say, all right, well, at A, what type of energy do you have? Well, maybe this one you don't have potential energy, but maybe this one you do, maybe this one you don't. But let's just say in general, you could have potential energy due to gravity at point A. Okay? You could have, it's definitely moving, so you're definitely going to have kinetic energy at point A. And then what type of energy could you have at point B? Well, you could also have potential energy. You could have kinetic energy. Now, here's the part and this is the part where fluid's a little weird, and this is why we have to deal with this. But like with this, if my pipe stays exactly the same width the whole time, well, that means the volume per time here has to be the same as the volume per time here, which means area times speed equals area times speed, which means the speed equals the speed. Ah! Well, what the heck? How could that be that the speed equals the speed? Oh, because there had to be some outside work done. Okay? And so normally when we write our equation, we go like this, and then we say, hey, was there any work done in between? And if it added energy, we would say, hey, plus work. Okay? If it took energy away, we would say minus work. And then you would end up, mathematically, it's going to be equivalent to moving it to this side of the equation. So because I don't know if it's going to add energy or subtract energy at this point, we're just going to say, I'm going to have some work over here, and I could also have some work over there. Okay? So here's my basic equation, and then again, this is just conservation energy. So I'm saying, I draw my picture, and I say, hey, what do I have? Well, I have potential, I have kinetic, I have work, okay? and at the different spots. But we're talking about, so let's write out our equation. So let's write this out. So you get mg, and then we'll call this y plus 1/2 mv, little v, speed, okay, kiddos, plus force times distance, and this would be at A, and this would be mgy at B plus 1/2 mv squared at B plus force times distance at B. All right, so all I did is just plug in my equations. But then you're going to be like, well, wait a second, we're talking about fluids. And we know when we talk about fluids, you know, typically we find mass by using this equation, where mass is going to be the density times, this is a big V, times the volume. So let's plug that in. So I'm going to have rho Vg here plus 1/2 rho V VA squared plus force. Now, let's do this too. Typically, when we're talking about fluids, we don't talk about forces. Most of the time, we talk about pressure. Well, how do we find pressure? Oh, yeah, pressure is force over area. So that means my force is really pressure times area. Does everybody see that? So I'm going to plug that in here. So I get pressure times area times D equals rho VGYB plus 1/2 rho VVB squared plus pressure, this would be all at A, okay, pressure at A at B times the area at B times D. Woo! That was a lot of writing. Woo! I'm getting tired. I'm gonna have to, stretch afterwards. Now, if you take a look, though, does everybody see that is right? That's volume. Okay. So this would be volume. This would also be volume. And look, volume, 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 which makes sense. That all has to be the same because remember, that's the whole the equation of continuity. That whatever the volume flow rate here has to be the same as there. So I can cancel all those volumes out. Goodbye, 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 and goodbye. And then lo and behold, I end up with the Bernoulli equation. Remember, that's speed. Speed. Okay. So here's all the Bernoulli equations is really saying, and when I do this, I think about it this way. I think it's like, hey, I realize this is not really energy anymore, but it came from potential energy, kinetic energy, and work. Okay? Potential energy, kinetic energy, and work. And again, I realize it's not actually energy. Like, it's actually the units for all of these things have to be pascals because we're adding them together. But they came from this equation of the equation of conservation of energy. So let me show you then how we can use this. So going back to my example with the paper, okay, if we do this, so I have my sheet of paper. So I'm just going to do this in a different color so you can see it. It's different. Here's my sheet of paper. I was blowing over top of the paper. So one of my points, I'm going to call it, is going to be point A. The other point is going to be point B right below it. Well, if you guys take a look, now here it looks like there's a height difference there. The height difference is the width of a sheet of paper. So essentially, here's what's happening. This and this are the same. So they cancel out. Okay, well, at A, I was making the fluid go faster. At B, the fluid was going slower. It really wasn't moving at all. It was in the room here. Well, if this has to equal this, if that's bigger, this has to be smaller, which means this has to be bigger. And if you remember, fluids always go from a low Oh, sorry, fluids always go from a high pressure to a low pressure. So that sheet of paper got pushed up because high pressure, low pressure. Just like wind. All right. Bye, kids.